The Simple Pendulum by Jesus Ramirez, Gerardo Mesa, and Valeria Dominguez. Here we have the index, first, the introduction, mathematical model, and at the end, our results and our conclusion.
Now, here we have the introduction. The purpose of this exercise is to enhance our understanding of linear second-order homogeneous differential equations through a modeling application involving a simple pendulum, which is simply a mass swinging back and forth on a string. And this model problem is representative of a wide variety of problems described by second order linear differential equations. We can see in the image the model, we can see the string, and we can see the mass.
Now we have mathematical model, period of oscillation of a nonlinear pendulum. Suppose that the pendulum is described by nonlinear second order differential equation. Here is the pendulum formula. We consider the oscillation under the following initial conditions. Here we observe the development of the formula. The angle alpha is the amplitude of oscillation. The order of the oscillation can be reduced if we find a suitable integrating factor. Multiply this equation by the integrating factor d alpha dt. This leads to the equation. Here is the formula. After integration, we obtain the first order differential equation. Given the initial condition, we found the constancy. Observe the formula and see some to gravity divided A, constant alpha. Then the question becomes the pendulum formula.
Next, we apply the double angle identity. Cosine alpha is equals 1 minus 2 sine squared alpha over 2, which leads the following differential equations. And as a result of 2 square root of g over L times by square root sine squared alpha 0 over 2 minus sin over alpha over 2. Integrating this equation, we obtain integral of d times alpha divided 2 over square root sine squared alpha 0 over 2 minus sine squared alpha over 2 equals to square root g divided by L integral dt. We denote sine alpha over 2 equals to k and introduce the new variable theta instead of the angle alpha. Then here we have another equation that it's equals to square root of y minus sine square alpha over 2 d times by alpha over 2 equals to square root of 1 minus k squared sine square theta d times by alpha over 2 equals to k cosine theta d theta. It follows that d times by alpha over 2 is equal to k cosine theta d theta over square root of 1 minus k squared sine squared 0. In the new notation or equation can be written as that formula as we can see. And next, we discuss the limits of integrations. The passage of the arc from the lowest point theta alpha equals 0 to the maximum derivations corresponds to a quartet of oscillation period times divided by 4. It follows from the relationship between the angles of theta and of alpha and theta that sines theta equals 1, and therefore we obtain the following expressions for the period of oscillation of the pendulum, as we can see in the other formula.
Now we can see the integral on the right cannot be expressed in terms of elementary functions. It's the so-called complete elliptic integral of the first kind. We can see the k and the integral of this variable. And the function k can also be represented as a power series, and we can see the power series, where the double factorials 2n minus 1 and 2n denote the product respectively of odd and even natural numbers. Note that if we restrict ourselves to the zero term of the expansion, assuming that k equals pi over 2, we obtain the known formula for the period of small oscillations. We solve this equation, and at the end we have that the period of each oscillation is 2 pi square root of L, that is the length of the string, over G, that is the gravity. So if we substitute with the data, we obtain that the period of each oscillation is 2 seconds.
Now we have experimental demonstration. In the experimental step on line about we propose having a simple pendulum with length some 1 meter. It follows directly that the period of the motion must be about 2 seconds. Notice that the period does not depend on the initial condition and the corresponding altitude on the motion. It will only depend on the gravitational constant g and the length of the string. Here we have the experimental demonstration video.
Here we have the results. A careful analysis of the video shows that 15 oscillations occurred over 30 seconds. We can estimate the average period by taking the total time in seconds and dividing by the total number of oscillations. T is equal to 30.4 seconds over 15, and it's equal to 2.02 seconds. This average period is found to be about 2.02 seconds, which is only slightly larger than our prediction of 2 seconds using the mathematical analysis above. If we break the video down into segments, we find that this average period t does not increase or decrease in any noticeable way. At first approximation, the period, and therefore the frequency, appears to be constant with time.
Finally, we have the conclusion. And to conclude this activity, we aim to illustrate how the modeling process with second or higher order differential equations is used to solve a practical problem. After solving the differential equation, we can predict the average period taking the total time in seconds and dividing it by the total number of oscillations and then verify it. Of course, according to the mathematical operations, it can be achieved what will be estimated period of each activity or at least a very approximate time. After having carried out the respective measurements and calculations regarding the simple pendulum and its relationships with the length, angle, and mass, it was concluded that the period of a pendulum only depends on the length of the string and the value of gravity. Since the period is independent of the mass, we can then say that all simple pendulums of equal length in the same place oscillate with equal periods. The longer the short length and the greater the period. And that's it. Thank you for your attention.